Good morning, dear abstract algebra students. So welcome to this instructional video where we would now discuss the concepts of groups and subgroups. So last time we have talked about binary operations and their properties. So we have talked about commutativity and associativity of binary operations. Now, if we combine a set together with a particular binary operation, we now call the combination as an algebraic structure. Okay, and then a group is an example of a binary structure. So when you say binary structure, there is a set and there is a binary operation defined in that particular set. Okay, so in activity 1, you were asked to find an element E in the set of integers so that if you add E to any element A, the result will just be A. That is A plus an integer, again A plus an integer, let's say blank, is equal to this same integer plus A. The question is what is this integer, so that the sum would go back to A. Okay, can you guess it? So the answer would be, since the operation here is addition, in other words, we say what do we add to A so that the sum is A, so that will just be 0. And there can only be one in such integer. So the question here, how many such elements are there? There is only one, only 0. Then consider the element 2, the integer 2. Can you find an integer x so that 2 plus this integer x will be equal to that same integer added to 2? That would give that number E, or that element E we found earlier. So we found it to be 0. So what number or what integer do we add to 2 so that the sum is 0? Okay, so you guess it right. That is negative 2. Negative 2 plus 2 is also 0. And there is also an one and only integer that can do this or has this property. Okay, actually these two properties here are actually properties of a binary structure. Okay, so we shall encounter this as we are introduced with the concept of groups, because these are properties of a group. Okay, so let us now formally talk about groups. Let's go to our book. So for this property, we have here the formal definition. Let S together with a binary operation asterisk be a binary structure. An element E of S is called an identity element for the operation if E operation S is equal to S operation E and both are equal to S. This is true for all elements S in the set. Okay, this E, this element that possess such property is what we call the identity element for the operation. Okay, now we also have said earlier here in the activity, there can only be one such integer. Only 0 can do this. Okay? That observation can now be uh, formalized by the theorem, by a theorem asserting the uniqueness of the identity element, meaning there can only be one identity element in a binary operation. I mean binary structure, if such an element exists. So we say a binary structure S with an operation asterisk has at most one identity element. That is, if there is an identity element, then it must be unique. Okay. Now for the proof, we shall follow the conventional proof of doing proof of uniqueness or showing uniqueness. So how do we show uniqueness? First, we assume that there are two of them. And then, we need to show that the two are just equal, meaning they are one and the same. Okay? So suppose there are two such elements. So let's say E and E prime or E bar in this book. Okay? There are two such elements, E and E bar, meaning for any element X, so if X is an element of the set S, it should be true that if you operate E to X, the result will always be X. Meaning, we say that X operation E should be equal to E operation X, and the result should be X. And at the same time, since E bar also possess the same property, the same characteristic, meaning if we operate E bar to X, it would yield the same result, meaning X operation E bar should be equal to E bar operation X, and that would again yield to X. Okay, but take note that X here can be any element of S. This can be any element of S, meaning E can assume X. E can assume X. So, or E bar can also assume X. Meaning, if X is substituted by E bar in the first equation, in this equation, let us call it equation 1. In equation 1, if we substitute X, so again, if X is E, because again, X can be substituted by any element in S. Substitute E for X in equation 1, we would then have, equation E bar. We substitute X by E bar in equation 1. So equation 1 will become E bar. So for that, equation 1 becomes E bar operation E should be the same as E operation E bar, and the result would be E bar. But for equation 2, so this is equation 2, X is substituted by E. So again, if X is E in equation 2, equation 2 will then become E operation E bar is equal to E bar operation E equals E. Now notice that we have obtained an equation E bar operation E equals E, and we also have here in the last part E bar operation E is E. But take note, the operation is a function, meaning this ordered pair can only have one image. If each image is E bar, and at the same time each image is E, and these two are not the same, meaning this must not be a binary operation, but it is given that this is a binary operation because we are talking of a binary structure here, meaning we can only have one image for the same ordered pair. So in other words, it should follow that E will be equal to E bar. Okay, so that goes to show that there is just but one identity element for a binary structure if that structure has a an identity element. Okay, so I hope you understood that. Next, okay. Now recall the concept of isomorphism. So last time, we say that when we say isomorphism, these are two structures which are basically the same. Okay? So let us take a closer look at an isomorphism. So a set S, so let's say this is S with elements, say A, B, C, and D, and another set S prime can only be isomorphic, meaning they will just be basically the same if they have the same number of elements. Diba, we said in the preceding video that we simply change the name of elements in S, meaning the number of elements in S should also be the number of elements in S prime, meaning S prime could have, let's say, the elements 1, 2, 3, and 4, and we simply change A to 1, B to 2, C to 3, and D to 4. In other words, we can make a one-to-one onto function from S to S prime. So let us call this function phi. Okay? Now, so we see that 1 actually is phi of A. Phi of A by our illustration is just equal to 1. Phi of B is 2, phi of C is 3, phi of D is 4. Okay, so there is a one-to-one onto function mapping S to S prime. But for this to be isomorphic, so if we would now be talking of binary structure being isomorphic, so meaning we now consider an operation for each set. If we now have an operation asterisk in the set S, so we define a binary operation here so that it becomes a binary structure, and we also have an operation asterisk prime in S prime. These two structure will be called isomorphic if and only if the function phi conserves the respective operations of the two binary structures, meaning if A operation B in S is equal to C, it should be that the image of A, phi of A, operation, since the image of A is now in S prime, so the operation will be asterisk prime, operated to the image of B should be equal also to the image of C, meaning again the function phi preserves the operations of the two sets. In other words, since C is just A operation B, again C is A operation B, so it should be that P of A operation B, this operation is in S, so that would be a asterisk as operation B. Phi of A operation B, which is C, should be equal to phi of A operation. This time this operation is defined in S prime, so this operation is asterisk prime, operation phi of B. That is what we meant by preserving the operations. The function preserves the operations of the two sets. So, for two binary structures, therefore, to be isomorphic, it should be that there is a one-to-one onto correspondence or function from one binary structure to the other, which preserves the operations of the two binary structures. Okay? So, phi here is called an isomorphism from S to S prime. Phi is an isomorphism from S to S prime. Okay, so you now know the formal definition of isomorphism. And if such isomorphism exists between S and S prime, that is when we say that S is just isomorphic to S prime and vice versa. The two binary structures will be isomorphic to one another. Again, what is that? If there is a bijection means an injection and a surjection at the same time, that is one-to-one and on-to at the same time. Function phi which preserves the operations of the two sets. Okay. Let us now proceed to this theorem, next theorem. Suppose the binary structure S with the operation asterisk has the identity element E for its operation asterisk. Now, if there exists phi mapping or pairing S to another set S prime is an isomorphism of S asterisk with S prime S asterisk prime, meaning if phi is an isomorphism, meaning this is a bijection from S to S prime that preserves the operations asterisk and asterisk prime of S and S prime respectively, then the image of E should also be the identity element for the binary operation asterisk prime on S prime. Okay? Since there is an identity element E for this binary structure, phi is a function from S to S prime. So E, since it is an element here, it has an image. It must have an image. So that image can be found in S prime. If E is the identity for S, its image, phi of E, is also the identity for S prime. That is what this meant. That is what is meant by this theorem. Okay? Let us now look at the proof. Let S prime be any element small s prime be an element of the set capital S prime. We must show that if we operate the image of E to S prime, the result will be S prime. Okay, for that to be, so that we can say that the image of E is the identity for S prime. Now, since phi is an isomorphism, it is a one-to-one map of S onto S prime. In particular, we can always find an element S, small s, in the domain so that its image is S prime. Okay, so we can always find an element S in S such that phi of S is S prime. Now, E is the identity element for asterisk. Meaning, if we operate it to S, okay, S, the identity element in S is E. So, S is in E. Meaning, if we operate E to this element S, it would satisfy the property of that of identity. So, we say E operation S will be equal to S operation E equal to S. Again, because E is the identity. Now, since phi is a function, then we would have, since these elements are just the same, S operation E and E operation S, meaning they would have the same images. And since this is equal to S, then that would be equal to phi of S. Okay? But since phi is an isomorphism, so it should preserve the operations, the respective operations of the two binary structures. Meaning, we can write this as phi of E operation, this time the operation in S prime is used, asterisk prime, phi of E operation phi of S is equal to, this can now be written as phi of S operation phi of E. Then we bring down phi of S. But take note, phi of S is S prime. Hence, we would get this equation here if we substitute phi of S by S prime. Therefore, indeed, the image of E in S prime is also the identity element for the operation asterisk prime in S prime. Okay, so that which is what we need to prove in this theorem. Okay. So, how do we show that one binary structure is not isomorphic? Okay. Take note, an isomorphism is a bijection, and at the same time, it should preserve the operation. Okay? Both conditions should be satisfied. Now, we know that both Q and Z, or rational numbers and the set of integers, are both countably infinite. We can count the elements, but we will not finish counting. So, they have the same cardinality. They have the same cardinal number. Meaning, we can always make a one-to-one onto function between these two. But, take note, the operation must be preserved. Take note, both operations are addition. Okay? But, x plus x equals c has a solution for the set Q. Okay, for example, for any rational number c, we can always find a rational number x, so that if we double that, the sum is c. Say for example 3. So the equation becomes x plus x equals 3. But this will just be equal to 3 halves. 3 halves plus 3 halves equals 3. Sorry. Three halves plus 3 halves equals 3. But take note, 3 halves is a rational number but not an integer. Meaning, this equation has a solution in Q, but it has no solution in Z. Therefore, the addition in Q and the addition in Z cannot be preserved by any bijection from Q to Z. Okay, why? Because this operation has a solution in Q, but it has no solution in Z. Okay? The same is true, same can be said when we talk of the binary structure, complex numbers together with ordinary multiplication, and the binary structure, real numbers with the same operation, ordinary multiplication. Note that the equation x times x equals negative 1 has a solution in C, which is equal to I, the imaginary number, because I times I squared is negative 1 in C, but there is no I in R, meaning it has no solution in R. Therefore, these two are not isomorphic. Okay? Next. Okay, let us now start talking about groups. We define a group as a binary structure as follows. A group G together with a binary operation asterisk of a set G closed under the binary operation asterisk. Actually, there is something redundant here. Because when we say binary operation, it is understood to be closed. Okay? Basta binary operation. So, this must be a binary operation in G. Meaning, it should be well-defined and closed in G. Such that the following axioms or properties are satisfied. G sub 1, for all A, B, C in the set G, we have the quantity A operation B operated to C should be equal to A operated to the quantity B operation C. Okay, quite familiar. That is just the associative property. Meaning, it should be that the operation is associative in the set G. Okay, that is the first condition. Second condition, there is an element E in G such that for all X in G, for any element X in G, it is true that E operation X is equal to X operation E and both are equal to X. Meaning, we can find an identity element in G for the operation asterisk. Okay, G has an identity for the said binary operation. And third, corresponding to each element A in G, meaning for every element A in G, there is an element A prime. We can find A prime. Some books denote it as A inverse. Okay, and this time we call it A prime. An element A prime also in G such that A operation A prime is equal to A prime operation A equals the identity element as defined in the second condition equals the identity element E. We call A prime as the inverse of A. So, first, we have the operation must be a binary operation, meaning closed and well-defined. The operation must be associative in the set. There should be an identity element in the set, and each element in the set must have an inverse, a corresponding inverse. Okay? So, it could be proven that the finite binary structure Z sub n under addition modulo n is a group. Let us show it here. Say for example, suppose we have Z sub 3. So that will be modulo 3, meaning the elements are just those numbers which are possible remainders when a number is divided by 3. So we have 0, 1, and 2. Note that if we add two numbers here, the result would still be in Z3. 0 plus 1 is 1, 0 plus 2 is 2, 1 plus 2 is 3, which is equal to 0 in modulo. 3. So the sum would always be found in Z. This is just to illustrate, not to prove. Okay? We are just trying to illustrate. So, addition modulo 3 is actually a binary operation in this set that can be actually shown using a table. So we have here the elements 0, 1, and 2. 0, 1, and 2. An addition table. But the operation here is addition modulo 3. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2. 1 plus 0 is 1. 2 plus 0 is 2. 1 plus 1 is 2. 1 plus 2 is 3. But that would give a remainder 0 if divided by 3. So that would be 0. Then 2 plus 1 is 0. 2 plus 2 is 1. Because 4 divided by 3 will give a remainder of 1. So you see that all results here, all results are elements of C3. So this operation is closed and well defined. Okay? And since addition is just associative, this is just a kind or a type of addition. And we know that addition is associative. So the associativity property is satisfied here. Then we have the elements 0, where any element in Z3 added to 0 will be the same element. Meaning 0 is the identity element for addition modulo 3. Also, each element has an inverse. Why? Because there is something that we can add to 0 to get a result of 0, which is itself. Meaning, 0 is the inverse of itself. Also, we can find an element added to 1 so that the sum is 0, which is 2. 1 plus 2 is 0, meaning 2 is the inverse of 1. There is also an inverse of 2 because we have here the result 0, meaning 1 added to 2 is 0. Therefore, the inverse of 2 is 1. Each element in the set Z3 has an inverse for addition modulo 3. So, this structure Z3 together with addition modulo 3 is actually a group. Okay? Now, sometimes we shall just write the group G with the binary operation asterisk as simply G. A group G. So, we do not write this symbol anymore. Sometimes it is already understood that there exists a binary operation in G when we say that G is a group, actually a group. Okay, so when we say a group G, so we do not say there is a binary operation there anymore. It's already understood. Okay. So, for example, we may refer to Z, Q, R under addition to be groups. Okay, additive groups to be particular or to be specific rather than writing them this way. Okay. Now, we have here the definition of an abelian group. We say that a group G is abelian if its binary operation is commutative. Okay, take note, if we go back to the definition of a group, the operation may not be commutative. Commutativity is not required for a structure to be called a group. Only associativity. But if commutativity is satisfied, then we say that such group is abelian. Okay, take note of that. It is not required of a group to be commutative. Okay, but again, if it so happens that it is commutative, the operation is commutative, then it is a special kind of group, which is called an abelian group. For example, the set of positive integers under addition is not a group. Why? Because there is no identity element. Addition. Okay, the operation here is addition. So the identity would be 0, but 0 is not in this set here. Okay, positive integers. There is no identity element for addition in the set of positive integers. Even if we include 0, so we say non-negative, the set of non-negative integers is still not a group. Why? Because although there is already an identity element, but some elements would not have an inverse for addition. Like for example, 2. Okay? Supposedly, if you want to add something to 2 so that the sum is 0, the answer should be negative 2. But then negative 2 is not in the set of non-negative integers. Okay, so it is important to note what set are you talking about. Okay, before you decide whether or not such structure is a group or not. The familiar additive properties of integers and of rational, real, and complex numbers show that these 4 sets are actually abelian groups. Okay? All of these are groups and addition. All of these are groups under addition. And addition is actually commutative in all these 4 sets. Meaning, these 4 sets together with addition is an abelian group. Then, the set of positive integers under multiplication obviously is not a group. Because although 1, the identity element for multiplication, is found in this set, the inverse of 3 under multiplication cannot be found in this set. The inverse of 3 is supposed to be 1/3. But 1/3 is not an integer. It is not a positive integer. Okay? Next, the familiar multiplicative properties of rational, real, and complex numbers show that these actually constitute an abelian group under multiplication. The same is true for non-zero sets Q asterisk, R asterisk, C asterisk. Okay? It can be proven that multiplication is associative in all of these sets. There is an identity. There is the identity element. 1 actually can be found in each of these. Then each element has its inverse. For example, 2 has the inverse 1/2 in Q plus. It also has an inverse in R plus. The same is true for this. Every element has its own multiplicative inverse in all these sets. So all of this constitute an abelian group under multiplication. Okay, let us now consider an operation which is not one of the 4 fundamental operations. Let us define a special type of operation. Okay? Here in example 4.14, we have an operation asterisk defined on the set of positive rational numbers by A operation B is equal to A times B over 2. But if A and B are rational numbers, the product is a rational number. That rational number divided by 2 would still be a rational number. Also, if both are positive, then the product would be positive. Meaning, this operation actually is closed and well defined. So, it is a binary operation. Okay? Now, note that if you have A, the quantity A operation B operated to C, by definition, A operation B can be written as AB over 2. Then, operate it with C. So, we'll have A over B, AB over 2 times C all over 2. Let us write it here. This one, AB over 2 would be AB over 2 operation C, so times C all over 2, which would be equal to ABC over 2 or ABC over 4. But ABC over 4 can be written as BC over 2 times A all over 2, which can be A operation BC over 2, which is just equal to A operation the quantity BC. Okay? For a more formal way of writing that one. So, for proving that one. So, we have the quantity A. So, there would only be one line, one story, because these are 2 sentences already. So, A operation B operation C would be equal to AB over 2 operation C, but that would be equal to AB over 2 times C over 2, which can then be written as AB times C over 2. I'm sorry, let's erase this. Over 2 all over 2. But this one, since multiplication is associative in the set of Q plus positive rational numbers, this one can be written as A times BC all over 2 over 2. Okay, so let's erase this equality sign. Which can then be written as A operation BC over 2. Or first, let's make it a bit detailed, more detailed. That can be A times BC over 2 all over 2. But this is just equal to A operation BC over 2. And BC over 2 is just B operation C. So we have A operation quantity B operation C. So that if we bring down the left side, we would be able to show that the quantity A operation B operated to C is just the same as A operated to the quantity B operation C. Hence, the operation is associative. Okay? Also, there is an element 2 in the set Q plus, so that if you operate it to any element A in Q plus, the result will be A. Why? Because 2 operation A, let's show it here. 2 operation A is equal to 2A over 2, but 2 over 2 is 1 times A, that will be equal to A. The same is true for A operation 2. So this shows that there is an identity element for the operation in Q plus, which is equal to 2. Okay. But how do we know that it is 2 in the first place? Let us derive it here. Okay. So formally, we would that could be better done. The proof would have been better done by writing first. Let E or let us go directly to the task. Find E, the element E, in Q plus. This is very important, that such element can be found in the given set. We need to find an E in Q plus such that let us make use of the symbol na lang. Symbol for such that E operation A is equal to A operation E operation E equals A for all element A in Q plus. Okay. But if E operation A is A, by definition of the operation, E operation A is just A. Operation is not commutative, so the order should be followed. Okay, this condition would mean that E A over 2 should be equal to A, because that is how we define the operation asterisk. So this means that if we multiply both sides by 2, we would get EA equals 2A. But take note that A is a positive rational number. It is a positive rational number. So the number 1 over A, therefore, would also be a positive rational number. Meaning, we say, but A being an element of Q plus would imply that the number 1 over A would also be an element of Q plus. So such number exists. Therefore, we can multiply such number to both sides of this equation. If we multiply both sides of this equation by 1 over a, so that would mean that EA multiplied by 1 over a will be equal to 2a multiplied by 1 over a, which will give E equals. Before we check whether or not such element would satisfy the property of being an identity element. Okay, so we now have here an initial value for E. Say initial because we are not yet sure. Okay, so we need to check. We now operate 2 to A in both ways. That is, show that 2 operation A is just actually A. Okay, so that will be 2A over 2. This is equal to A. And at the same time, A operation 2 is equal to A times 2 over 2. But 2 times 2 over 2 is 1. 1 times 2, A times 1 is A. Oh, this is not 2, that is A. Sorry. That is actually A. And this is also equal to A. Therefore, we can now formally say that Q plus has an identity element ID element 2 for the defined operation asterisk. Okay. Then finally, we can say that for every element A in the set of positive rational numbers, we can find a corresponding inverse 4 over A, so that if you operate it to A, the result will be the identity element 2. Okay, this can be shown formally as follows. We do it similar to how we prove the existence of an identity element. So we say find an element, or let's say given A. Let us first take an arbitrary element of the set. Given A in the set Q plus. We need to find A prime in the same set, A prime in Q plus, such that A operation A prime is the same as A prime operation A, which both yields the result the identity element which was found earlier, which is 2. Okay, so this is what we have to do. We look for A prime. But if this is true, that A operation A prime is 2, so this would imply that A prime over 2 is equal to 2. Okay, this one, which by definition of asterisk is A prime, A times A prime over 2, is just equal to 2. And if we multiply both sides by 4, we would get A prime, this is A, okay? A prime is equal to 4. And since A is a positive, take note, A is a positive rational number. Again, if A is a positive rational number, then there would exist a positive rational number 1 over A. We can multiply both sides by 1 over A, giving us A prime to be 4 over A. So the inverse therefore of A is 4 over A for the operation asterisk as defined. Okay? So this therefore is the initial value for the inverse of A for a given A. Next thing to do is to show indeed that that is the inverse. So how do we do that? So we have A operation 4 over A would be equal to, by definition of the operation, said to be A times 4 over A over 2, because that is how definition was defined. But then A over A is 1 times 4, so that will give us 4. Then copy over 2, so 4 over 2 will just be equal to 2. So indeed A operation, this expression equals 2. At the same time, A over 4 over A rather, 4 over A operation A will be equal to 4 over A times A penmanship is terrible over 2, but this again would yield 4 over 2 equals 2. Hence, we have shown that, so we say that it will imply that for every A in the set, plus for every A in the set, rational numbers which are positive rational numbers, there exists an A inverse in which is equal to let us just write this here below. For every element A in the set of positive rational numbers, we can always find an A inverse which is equal to 4 over A which is in the same set such that A operation A inverse, this is A, yeah, A, is equal to A inverse operation A, which is equal to the identity element 2. Okay, so by the preceding arguments, the proof for associativity, the proof for the existence of an identity element, and the proof for the existence of an inverse for each element of the set, we hence say that the set of positive rational numbers with the operation asterisk constitutes a group structure. Okay, next. We now have here the elementary properties of groups. By the way, there has been no definition for a subgroup yet. So we can just think of the similarity of sets and subsets to groups and subgroups. When you say set, a subset is a set within a set. Therefore, a subgroup actually is a subset of a group which is also a group. Okay? So, for example, we know that the set of the set of integers is a group under addition, but that is just a subset of a larger group, which is the set of real numbers under the same operation. Okay, we are talking of the same operations here. So we say that this is a subgroup of that larger group there. Okay, so a subgroup basically is just a group within a group, or a group contained in a larger group. But take note that their operations must be the same. Okay, they would have the same operation. So you define this as the induced operation from one set to its subset. Okay, first elementary property of a group, we call it the left and right cancellation laws. So if G is a group with a binary operation asterisk, then the left and right cancellation laws hold in G. Meaning, if you have the equation A operation B equals A operation C, A here can be cancelled. Okay? That is called the left cancellation. Meaning, this will just become B equals C. And also, similarly, B operation A equals C operation A should imply that B equals C for all elements A, B, and C in the group. Okay, so let us prove this. The first one. If this is true, then this must be true. So suppose this is true. Suppose A operation B is equal to A operation C. By property 3 of a group, A, since A is an element of the group, then A must have an inverse. Okay, so if we operate the inverse A prime to both sides, we will have A operation quantity A operation B equals A inverse quantity A operation C. Take note, we operate at the same side. If we operate A inverse to the left, it should be operated to the left here. Okay, not to the right because the operation is not necessarily commutative. Okay, the order of operation in the left side of the equation should be the same as the order of operation in the right side. Okay, but by the associative property of the operation, we can write this as the quantity A inverse operation A operated to B equals the quantity A inverse operation A operated to C. But A inverse operation A, by definition of inverse, this is just E. So this is E, this is also E. So we'll have E operation B. The right side will be E operation C. But by definition of E, the identity, so this will be equal to B, and this is equal to C. Therefore, we'll have B equals C. In other words, we say that if it is true that A operation B equals A operation C, it should follow that B equals C. Okay? The right cancellation law, that is, if B operation A equals C operation A, then B equals C, can be proven in a similar way. Next, we now have theorem 4.16, solutions to linear equations. If G is a group with a binary operation asterisk, and if A equals B, then any elements of G, if A and B are any elements of G, then the linear equations A operation X equals B and Y operation A equals B have unique solutions X in and Y in G. Meaning, we can always find a value for X that would satisfy these two equations. This one and this one. Okay? So here, the solution has already been obtained. It is said to be A inverse B. Let us show first how it was obtained. So again, the equation is A operation X equals B. So we need to find X. Question is, what is this X? Then show that X is in the group. It is in the same set. Okay. Now, if we operate both sides by A inverse, there at the left side. So A inverse operation quantity A operation X A operation X must be equal to A inverse operation B. But by associativity of the operation, we can write this as A inverse operation A operation X should be equal to A inverse operation B. But by definition of inverse, this will just be equal to E operation X. Because that right side there. But E operation X is X. So X is obtained as A inverse B. So that if you operate it, or if we substitute it to X, we'll have this result. Hence, X here, this value of X satisfy the equation, meaning the value X, A prime or A inverse B is a solution to the linear equation. Okay? In a similar fashion, we can also find a solution for the second linear equation to be B operation A inverse. So, there is always a solution to a linear equation in a group. Now, we found a solution. How do we show that it is unique? Again, to show that an element is unique, assume that there are two such elements and simply show that they are equal. For example, here we have, suppose there are two solutions for that particular second linear equation. Suppose there are two solutions, y sub 1 and y sub 2. Meaning, y sub 1 operation A equals B, B, and y sub 2 operation A equals B. Both are equal to B, meaning they are equal. Y sub 1 operation A equals y sub 2 operation A. Operate both sides by A prime, or actually this can be applied with the right cancellation. Using the right cancellation law, we cancel A. Well, what will be left would be y sub 1 equals y sub 2. Meaning, there can only be one solution because we assume that there are two, but it turns out that they are equal. Okay, the proof for the uniqueness of X here will be done in a similar manner. Next theorem. In a group with binary operation asterisk, there is only one element E in G such that it satisfies the property of an identity element. Actually, this part here has been proven already earlier in theorem 3.13. Okay, the uniqueness of an identity element. What remains to be proven is the second part. Okay? So, again, uniqueness of an inverse. Suppose there are two inverses, A prime and A double prime. Meaning, since A prime is an inverse, it should follow that A prime operation A equals A operation A prime and both are equal to E. At the same time, because A double prime is also an inverse, so we say that A double prime operation A is equal to A operation A double prime, and both also are equal to E. These two equations are both equal to E. See here. Meaning, this expression and this expression are both equal to E, meaning they are equal. Okay? So, by the left cancellation, you can cancel A there because we are talking of a group. Therefore, we say that A double prime is just equal to A prime. So, there can only be one inverse for each element in a group. Okay. We also see here that if we operate B prime or B inverse operation A inverse to the quantity A operation B, we would come up with E. Meaning, this expression here is the inverse of A operation B, written in the formally in this corollary. Okay? The inverse of the quantity A operation B is B inverse operation A inverse, as shown in this argument here. This is the proof actually of corollary 4.18. Okay, other weaker binary structures are derived from the idea of groups. They are called semi-group and monoid. Okay. A semi-group is a binary structure with an associative binary operation. whereas a monoid is a semi-group with an identity element. Okay, so a semi-group has an associative operation but not necessarily has an identity element. If it has an identity element, it becomes a monoid. If a monoid has inverses for each element, then the monoid becomes a group. Okay? In other words, a group is always a semi-group and a monoid at the same time. A monoid is a semi-group, but not all semi-group are monoids. Okay, I hope that is clear. Let us now proceed to finite groups. Is it possible for a finite set to constitute a group structure? Actually, yes. Okay. Now, if it is assumed that the group only has one element, take note that by one of the properties, a group must have an identity element. So if a group has just one element, such element should be the identity. Okay? Wherein its a product when operated to itself would be itself because there are no other elements. But E is the identity, meaning the inverse of E is itself. And this would constitute actually is of a group. Okay, so there is a group with one element as shown in this table. Okay, now what if there are two elements? If there are two elements, then it should be that one of the two is the identity. So there is an identity element and another element, let's say A. Okay, shown in this table. Now, take note that E should be the identity. Meaning, E operation A must be E. E operation A must be A. Also, A operation E should be equal to A. Now, A must have an inverse. Meaning, we have to get an element operated to A so that the result is E. Meaning, E should be found in the row containing A and the column containing A. Again, E must be somewhere aligned with A horizontally and aligned with A vertically. There should be an E somewhere there. But note that there is only one blank space, meaning there is no other space left but here. So that is where we put E. Therefore, we see that the inverse of A is itself by this table. We cannot form any other group structure with two elements other than this. Meaning, there can only be one group with two elements as shown by this table. Except if we rename the elements. Instead of E and A, we say 0 and 1. We would have the same table. Actually, this is just the addition table for Z2. Okay, under addition modulo 2. So this is the group table for this such group. Okay. So all other groups with the same number of elements should just be isomorphic to Z2. Next, if we would have three elements, but take note here that it is not only that E can be found in each row and each column. Take note that in the preceding theorem, the equation A operation X equals B must have a solution. Meaning B should be found aligned with A horizontally and aligned with A vertically. And this is true for every element A and B of the of the group. Meaning, each element, therefore, each element of the group can be found in each row and each column. There should be a B in each row, and there should also be a B. Again, this would imply that there is a B along A. So if this is the group table, this here element is A, we have something. There must be an element here somewhere, X, so that the answer is B. So B should be found here. So aligned with A horizontally. Also, we have Y operation A equals B. So, meaning, if this is A here, there must be some element here, Y, so that Y operation A is B. Meaning also, B should be found aligned with A vertically. And take note again that these are elements, arbitrary elements in the group. In other words, every element of the group should be present in each row, and it should also be present in each column. Okay? So that if we are to form a group with 3 elements, let's say E, because we have to be sure that there is an identity element. Then another 2 elements, let's say A and B, in this group table. Since E is the identity, so automatically this would be E, A, and B. A operation E should also be A. B operation E should be B. Okay. Now, again, each row in each column should contain every element in the group. Here, we lack E and B here. Okay, so this would be the slots for E and B. We cannot put B here because if we put B here, there would only be one remaining slot for 2 elements A and E. See that? So B cannot be here. There would be no other place for B but here. Therefore, meaning they should be E. At the same time, this column only has 1 slot for E, and in this row we have 1 slot for A, which would make A, B, and E present in the last column. So there are no other way that we can form a group of 3 elements. So there is only one group structure of 3 elements. Actually, that is just the same as the group addition modulo 3, C3. Okay, if we would recall such group, so we have 0, 1, and 2, 0, 1, and 2. 0 is the identity, so this is 0, 1, 2. 1 plus 0 is 1, 2 plus 0 is 2, 1 plus 1 is 2, 1 plus 2 is 0, 2 plus 1 is 0, 2 plus 2 is 1. So if we would compare, actually the 2 groups are basically the same. We only have renamed E as 0, A as 1, and B as 2. We can see here there is a B in this diagonal, 2 in this diagonal. We have E, E, so we have 0, 0, 0. Okay, so they are just the same. There. You can experiment for groups with 4 elements, okay, on your own. Then we shall have a chance to discuss that when we move on to finite groups, formal discussion of finite groups. So that ends the discussion with respect to groups and subgroups in this book. Let us go back to our module. So here in activity 2, you are asked to determine whether the operation gives a group structure on the given set. Okay, so that is activity 2. The solutions are actually below. Okay, so we have first the operation asterisk defined on the set of integers by letting A operation B equals B. So this is just usual multiplication in the set of integers. Okay, we know that it is closed, well defined, because any integer multiplied by another integer is still an integer. Hence, the operation is a binary operation. The associative property of multiplication in the set of real numbers would imply that it will also be associative in the set of integers, since the set of integers is a subset of R. And there is an element 1 in the set of integers, where if we multiply it to any element x, the result will be x. So there is an identity. However, there is no inverse for some elements in the set. Say for example 2. Supposedly the inverse of 2 under multiplication is 1/2. But 1/2 is not in Z. Okay? Therefore, so this would not be used actually in the verification. We simply show a counterexample because we disprove, okay, that it is not a group. So we show that there is an element 2 with no inverse. So that the operation does not give a group structure on the set Z. Second, let asterisk be defined on the set of even integers, meaning these are integers of the form 2n, where n here is an integer, meaning there's the elements of this set are multiples of 2. Now we define addition. Okay, so this is just ordinary addition on the set of even integers. So if a and b are even integers, are elements of 2z, so we can find integers n sub 1 and n sub 2, so that a is equal to 2n sub 1 and b is equal to 2n sub 2. So if we add the two, if we operate a operation b will just be a plus b, or that would be by substitution 2n sub 1 plus 2n sub 2. So there is a common factor 2, so we have 2 times the quantity n plus 1, n sub 1 plus n sub 2, which is still an even integer, meaning it is closed and well defined in the set of even integers. Thus, the operation is a binary operation. But observe that the set of even integers is just a subset of Z. And addition actually is associative in Z, meaning it should also be associative into Z. Hence, the operation is also associative into Z. Also, we have an even integer 0. Even because it can be expressed as 2 times 0, and 0 is an integer. Okay, and note that if we add 0 to any positive integer a, any even integer a, the result would always be a. So 0 is the identity element for 2z for the operation asterisk. Then if a is an element of 2z, then there is an integer n sub 1 where a is 2n. Let us now try to find an inverse of a. But note that we are talking here of addition. The inverse will just be the negative of the number. So note that the negative of A, which is equal to 2 times the negative of n sub 1, and if we add that to A, we would always get 0. Meaning, every element in the set 2Z has an inverse for the operation. All of the properties of a group are satisfied by this structure, meaning this would give a group structure. Okay, 2Z with the ordinary addition. Next, the operation asterisk on positive real numbers defined by A operation B equals the square root of A times B. Okay, so here we have, let A and B be positive real numbers. So this would mean that they are both greater than 0, which would imply that their product is also greater than 0, and that their square root is therefore greater than 0. Meaning, the square root of A times B, which is defined as A operation B, is also a positive real number. Hence, it is an element of R+. So we say that the operation is a binary operation on R+. However, if we check associativity arbitrarily for elements A, B, and C, it would be hard for us. So it would make us suspect that the operation may not be associative. Indeed, it is not. So if we take, showing a counterexample, if we take the real numbers, positive real numbers 2, 3, and 4, we have 2 operation quantity 3 operation 4, we would have 2 operation 3 operation 4 will give the square root of 12 based on the definition. So we have 2 operation square root of 12. So which would give us the square root of 2 times the square root of 12. Okay, the square root of the quantity or the square root of the product, 2 times square root of 12. But then 12 is 2 square root of 3. So this can be written as the square root of the product 4 times the square root of 3. But the square root of 4 is 2. So we have 2 times the square root of 3. That is why we have here 2 times the 4th root of 3. Okay? Again, let me clarify that. The square root of 4 is 2. So this will become 2 times the square root of the square root of 3. That is why we have here 2 times the 4th root of 3. However, if we rearrange the grouping and consider 2 operation 3 first, we will have the quantity 2 operation 3 operated to 4, which would give us the square root of 6 operation 4, which would be equal to the square root, actually it has been reordered. This one should have given us the square root of 6 times 4, which may be written as this one, the square root of 4 times the square root of 6. But again, the square root of 4 is 2, so that would be 2 times the 4th root of 6, which is not equal to 2 times the 4th root of 3, meaning this expression is not equal to this expression. So we have this one. That means to say that the operation is not associative. Therefore, we don't have to proceed to the proof for the existence of identity and inverse. We can directly conclude that the operation does not give a group structure in the given set, positive real numbers. Okay, that ends the lesson. If you have some questions, you can ask me through our group chat. Also, again, you may want to subscribe in my YouTube channel and click the notification button for you to be notified whenever I upload uh, instructional videos for abstract algebra. Thank you for your attention and good day.